Hello, so today we're going to talk about roots and zeros. We're going to discuss the ways we can use our synthetic division to identify if we have roots or zeros of a function. Then we're going to talk about other ways we can look for roots and zeros of certain types of functions as well. If you're following the textbook, in the Glencoe Algebra 2 2018 edition, we're in sections 4.8 and 4.9 on page 287 and 293. So the factor theorem tells us that we have a binomial, x minus r, where r would be, then the solution. This would be a factor of the polynomial p of x, if and only if we get a remainder of 0 when we use the synthetic division with this binomial. So all those different times we did synthetic division, we were getting zeros for our remainders. That implied then that the binomial term was a factor. And then the resulting polynomial that comes from that after a remainder of 0 is then something we can then factor further to find all solutions. So we have this right here. We're given a polynomial function, x cubed minus 7x squared plus 7x plus 15. We're told x minus 5 is a factor. So we want to use this factor to first prove it's a factor by getting a remainder of 0, and then from there finding the remaining factors. So for problems like this, if you don't get a remainder of 0, that should be a sign that you set it up incorrectly. So, since it's x minus 5, there'll be a 5 on the outside of our bracket. And then we have 1, negative 7, 7, and 15 on the inside. And again, we apply synthetic division. We carry down the 1, multiply the 5 and 1, add the negative 7 and 5, multiply again, add, and then multiply. And we see we do get a remainder of 0. So this tells us right here, since that's a remainder, constant, x and x squared, that this cubic is x minus 5 and then x squared minus 2x minus 3. Well, that quadratic we can now factor using our factoring methods. So we know if it's x squared, the first two terms are x's. Negative 3 implies we have a positive and a negative. And then in order to make sure they multiply to be negative 3 and add to be negative 2, we need a negative 3 and a positive 1. Well, those are all the remaining factors, which would mean the solutions would be 5, negative 1, and positive 3. We will eventually talk about how to find the factors on our own without being given something, but for right now you're always going to be given the one factor. Our job is to prove it's a factor and find the resulting quadratic or cubic, whatever it happens to be, and then factoring it further. Alright, so let's try that again. So we have, for this one, x cubed minus 7x squared plus 4x plus 12. We want to prove that x plus 1 is a factor. So since it's x plus 1, we'll have a negative 1 on the outside. And then 1, negative 7, 4, and 12 on the inside. So as we go through synthetic division, we find, as we work through this whole thing, that we get a 0 for our remainder. And again, remainder, constant, x and x squared. This tells us that this would have factored to be x plus 1, and then x squared minus 8x plus 12. Well, we have a quadratic which we can now factor further. Since it's x squared, we'll have x's in both spots. The positive 12 tells us they're the same signs, and they're both negatives because of the negative 8x. And the two numbers that multiply to be a positive 12 and add to be negative 8 are negative 2 and negative 6. Which means our solutions would have been negative 1, 2, and 6. Technically, when you work through these, the quadratic doesn't necessarily have to factor. So you might have to use stuff like the quadratic formula or complete the square to find your solutions. For our purposes, though, all of them will factor. So again, the given factor has to give you a remainder of 0. And then the resulting quadratic has to factor out. If neither one of those two things occur, that is then a mistake on your end. Your job is to then look back and try and figure out what the mistake is. Now, if we have a number in front of the x cubed, we still go through the same process of our synthetic division. Just going to mean the resulting quadratic will be a 2x squared term. So again, the 4 is on the outside. 2, 7, negative 53, negative 28 on the inside. As we go through our synthetic division, we again get a remainder of 0. It tells us this factor to be x minus 4, 2x squared, plus 15x plus 7. So from here, you're going to have to factor that quadratic, go through your grouping method. When you do that, you'll find that you're going to get 2x plus 1 and x plus 7 as your two factors. Which means our solutions would have been 4, negative 1/2, and negative 7. Alright, so that's what I want you to do when you're given a polynomial and given a factor. Prove it is a factor and find the remaining ones. Synthetic division for the first step, and then factor the quadratic for the second step. Now, what we have right here is what we call Descartes' rule of signs. So this tells us how many positive and negative zeros can exist in our function. Again, so as we go through it, it says the number of positive real zeros of p of x is the same as the number of sign changes in the coefficients of the terms, or less than this by an even number. This means if there are 4 sign changes, we could have had 4 positive zeros, or 2 of them, or 0 positive zeros. Solutions. And then for the negatives, it's the same idea, but we have to do it as p of negative x, so we technically have to change the variable there. You'll find that it'll just simply be the opposite of what's happening with the positive zeros. So let's kind of practice that out. So we're given an original f of x function, and we want to count the number of sign changes to see how many positive zeros occur. So we notice that's a no. That didn't change sign, it's positive to positive. Positive negative means yes. Negative to negative is no. Negative to positive is yes. Positive to negative is yes. Negative to positive is also yes. So our positive zeros, we have 1, 2, 3, 4 yeses, so it could be 4, 2, or 0. Now, for the negative possibilities, well, we count the number of no's. There are 2 no's, there could have been 2 negatives or 0 negatives. Again, we're decreasing by an even number. So we just simply decrease by 2. That's all you have to do to work out the number of positive or negative real zeros, count the yeses for positive, and count the no's for negative. That will tell us the maximum that could occur. And then we decrease each of those numbers by 2 until we get down to 0, or we get down to a 1 if we had like 5 positive zeros. Now for the imaginary ones, we simply start off with the maximum even exponent we have. Now we notice our highest exponent is a 6, and that's even, so that means we could have had 6 imaginaries, and we then decrease that by 2, so 4, 2, or 0. So that would represent the total number of imaginary solutions that could have occurred with this particular equation. We're not saying that there are 4, 2, 6 imaginary, we're not saying any of that. We're just saying this is the maximum that could occur based off this. Maybe this function has 2 positives, 2 negatives, and then it has 2 imaginaries. Cool. Maybe it has only 0 positives, 2 negatives, and therefore it has 4 imaginaries. Either way, it has to total out to 6, but there's many different ways this could have occurred. Imaginaries will always be with even, because they have to have its conjugate to be a solution. So you'll never have an odd number of imaginary solutions, because that will not give a polynomial function. So if we have this one right here, again, we're counting yeses. So no sign change, no sign change, yes, no, and yes. So for our positives, we see that we have 1, 2 yeses. So the total possibility for positives is 2 or 0. Our negatives, we have 1, 2, 3 no's. We could have had 3 negatives or 1 negative. Again, we have to end once we get to a 0 or a 1, because we can't have less than 0 solutions. And if I decrease 1 by 2, we'd get a negative, and that doesn't make any sense. And then imaginaries, again, we start with the maximum even exponent we have. Our highest exponent is 5. That's not even, so then we take a look at 4. So we could have had 4 imaginary solutions, and then decreasing that by 2's gives us 2 and 0 as well. So that's how we're using Descartes' rule of signs, counting yeses for positive, counting no's for the negative, and then the maximum even exponents for the imaginaries. And that gives us the highest value for each of those. Positive 2, negative is 3, imaginary is 4, and then we decrease it by 2's until we get to 0 or 1. Now, we were talking about just before the whole conjugate theorem idea. So this is dealing with the idea that if we have a conjugate, an imaginary zero, we have to have its conjugate as well. We can't just have an odd number of imaginary solutions, because it will not give us a polynomial function that actually works out. So the example they use is if 3 plus 4i is a 0 of this f of x function, then 3 minus 4i has to also be a 0. And we'll use this idea to write out our polynomial functions themselves. So we want to write the polynomial function of least degree with integral coefficients that have the given zeros. Now when we say least degree, we're meaning we don't want any double or triple roots. So if -1 is a solution, we're not assuming it's a solution like 4 times kind of thing. We're only assuming it's a solution once. And then on top of that, integral coefficients mean we're assuming that there are no fractions technically in front of these numbers to work out. So we're just going to assume that it's just nice factors and there's no other number that could have factored out from the expression. So we're told we have -1 is one solution, and then 5 minus I is another. Well, that means then 5 plus I is a third solution. It's conjugate. Now to write this out, we write them in their factored forms, so it'll be x plus 1, and then x minus 5 minus I, then x minus 5 plus I. We're always going to have the opposite sign for the number. So since it's -1, that's why it's plus 1. Since it's a positive 5, that's an I, it's -5. And then we'll alternate the signs for the I so that they are proper conjugates. So now we need to FOIL this out. Now, as far as foiling goes, you should always FOIL the imaginary factors first, because you should find the imaginary parts cancel out. If they don't, then look back at how you wrote it, look back at how you FOILed it, something went wrong. So again, so we have x plus 1 in the first spot, and then as we FOIL the x minus 5 minus I and x minus 5 plus I, we're going to get x squared minus 5x plus ix minus 5x plus 25 minus 5i minus ix plus 5i minus I squared. And if you look at each one of our I terms, I've got a positive ix and a negative ix, so they cancel. I have a negative 5i and a positive 5i, so they cancel. And the negative I squared becomes positive 1. So now when we combine like terms in that quadratic, we have x plus 1 still. Now we have x squared minus 10x plus 26. As we can see, all the I terms went away. We now have a quadratic, which can now FOIL nicely with the x plus 1 to make x cubed minus 10x squared plus 26x plus x squared minus 10x plus 26. So we combine like terms to get x cubed minus 9x squared plus 16x plus 26. And that would be the solution, the original polynomial function that has the least degree and integral coefficients. Again, theoretically, these three solutions could have worked if we had like double and triple roots in different locations. That's fine. We're not stressing over that. We just want to simply rewrite it as the least degree function. Okay, so let's take a look at another one. So we have 2 and then 1 plus 2i. So when we work this out, we know that it has to be a 1 minus 2i. So we'll get it to be x minus 2, x minus 1 plus 2i, and x minus 1 minus 2i. Again, always the opposite for the number and alternating for the i's. So when we FOIL the I expressions, we're going to get x squared minus x minus 2ix minus x plus 1 plus 2i plus 2ix minus 2i minus 4i squared. Notice 2ix and 2ix, they cancel. 2i and negative 2i, they cancel. Negative 4i squared becomes a positive 4. So we can get the quadratic x minus 2 times x squared minus 2x plus 5. Nice quadratic, no more imaginary solutions. So that FOILs with the x minus 2 to get x cubed minus 2x squared. I'm really sorry about all these lines that just kind of form. Plus 5x minus 2x squared plus 4x and then minus 10. So we'll combine to get x cubed minus 4x squared plus 9x minus 10. Again, I'm not really sure what happens with those lines. I'm not like suddenly just shooting a line upward. Just kind of an error with the pen. Anyway, so there's our our cubic function. You can be given as many factors as you want. It could be 4 factors, it could be 7 factors, it could be anything we want. Though obviously I'm not going to go too crazy. You'll generally be given 2 factors. You'll have to recognize the conjugate for the one imaginary solution. You might be given a total of 4 factors after you include the conjugate. It's still the same thought process. Always fool the imaginary terms first. That way you get a quadratic that has no more i's, and then just fool the rest of the expressions from there. Alright, so that's it for roots and zeros. So next time we're going to talk about how to solve a polynomial function from scratch, not being given a solution to begin with like we had in the beginning here. You just have to find them on your own. But thank you for watching, and I'll see you next time.